Okay, here's the other section on valency and what it means. Now this time I've taken the slice of the cake because again we're looking at forming of compounds. It's like making a cake. If we want to make the right compound, we have to put things together in the right order and the right amount. So let's go back to the basics. We've learned already that atoms have positively charged nucleus containing protons and neutrons, and they have electrons moving around that nucleus in energy shells or energy levels. Now the outermost energy level, the way we have the electrons, is called the valence shell, and this is the one we've used when we've been doing things like Lewis diagrams. We've actually only been concentrating on the elements in the valence shell, and we will do that again because the valence shell helps us work out the charge on the ion. We've also seen that having an empty or full valence shell in our study of the first 20 elements of the periodic table, that we've had a stability that comes with it. And this is typified that all of the situations where we've got full or empty shells correspond to inert or noble gases. Now, valency in a nutshell is how many electrons need to either enter or leave an atom to give it this full or empty shell. So that decides the same as the charge on the ion. This is why they are linked together. And we can see that we can work it out to give the same electron structure as a noble or inert gas. Now to help us out, the people who created the periodic table actually have made it very easy for us. And what they've done is we look at the group number. Now we're not talking about, on some periodic tables you'll see the group numbers go to 18. On others they go to 8. Now we're talking the long groups, so the long columns, the full size columns, not the transition metals. We'll go to them later on. And we can see that for metals, the group number corresponds to the valency. So we've got the group number 1, which is the alkali metals, have a valency of 1. They also have 1 valence electron. Sounds good. Group number 2, or the alkali earth metals, have 2 valence electrons. Alright? So they have a valency of 2. Easy peasy. But we get into problems when we go to the other side of the table, when we go to the non-metals side. If we go to the halogens, now they're in group number 7. That means they've got 7 electrons, but it's so much easier for them to only have to gain 1 to fill it than it is to lose a 7. So we tend to find that for non-metals, the valency corresponds to not how many electrons they have, but how many electrons they need to fill the shell. So I like to think of it as 8 minus the number of the group. So in our case, when we go to and have our halogens, group number 7, it's 8 minus 7, or 1. So all the elements in the halogens have a valency of 1. Now if we go to the next one next to it, which is the oxygens group, they have 6 electrons, so they need 2 to fill, so it's 8 minus 6, or 2, is their valency, and it seems to work out nicely for us. Now the transition metals are the problem. They're the short columns in the middle of the table, and they can have more than 1 valency. So we have to be very, very careful with it, and what we have to do whenever we are naming or thinking about a transition metal, we should see that in brackets after its name, it will have its valency. For example, you might see iron in brackets in Roman numerals 3. That tells me the valency of the ion in this particular compound is 3. You might have gold 1 or silver 1, and that tells you the valency in that particular compound of those elements is 1. But in general terms, all of the transition metals will have a 2+ valency, and they will have at least 1 more. Now as you get a bit further down your study of chemistry, your teacher will start to refer to things like oxidation numbers, and that is a bit more involved, and we'll leave that till that time occurs. Right, so let's go through the examples. Sodium is an alkali metal. It's found in group 1, so it will have a valency of 1. Right, metals have the valency corresponding to the number of their group. If we go to the next one over, next column, we've got an element called calcium, and it's an alkali earth metal. Notice the difference in name, different group, different number of valence electrons, different valency, and in this case it is 2. Now calcium's relations like magnesium, barium and strontium will also have a valency of 2. If we then go across the table to oxygen, and we are also talking about sulfur, another common element found in that group, they are in group 6, so the valency will be 8 minus 6. As I said before, it's the number they need to fill to get to 8, so that would be 2. And our last example, of course, is in group 7, or the halogens. A very common element is chlorine. It's found in 7, and chlorine and its relatives fluorine and bromine and iodine will all have the same valency, and that will be 8 minus 7, or 1. And this tells us how many of each one of these we can mix together to form compounds. But that's another story, and that will be taken up in another short video.